Hey guys, can you hear me?
Yes.
Any questions before we get started? Okay, guys, then let's get the show on the road. Last week of classes, and we are not going to go through new material this week. We're just going to be looking at some of the exam problems, and whatever questions or concerns you might have, you will have plenty of opportunity to ask about questions. So if you haven't signed up for the oral exam, you need to do that soon. If you have signed up for the oral exam, please go check the announcement and make sure that your name appears where you think it should. In case there is a typo or a mistake on my end, just let me know about it. Okay. Are there any questions before we start solving some problems? The syllabus has been updated, so if you grab the latest version of the syllabus, you can see all the sections that we have talked about. It's on one of the last pages. Maybe I could share that so we can just see it together. If you go on the last pages of the syllabus, you'll see here. So we are here around week 14. We are solving exam problems, and then week 15 is when the oral exams are taking place, and you can see all the chapters listed here. Okay, if there was a question in the, can you explain a little bit of homework 2, homework 10, question number 2? Yeah, we can start there. We can start there. So let me bring up the homework. Bring up the homework number 10. Yep. So it's Alice who's asking. Oh. Okay, so number 2. So bring up my document camera and then we can all see it. So this is actually an old interview question. It's an old interview question a student came back with. It said he was asked something along these lines for a quant job. And so there's a payoff, there's an option payoff. It's an option payoff at time 1. pays off the difference between two stock prices. Pays off S hat 1 minus S1 plus the bottom. So we have two stock prices, so we write down the dynamic. So it's DST. This is equal to ST. And we are already writing the dynamics under the risk neutral measure. We know that under the risk neutral measure, discounted stock prices are martingales. Equivalently, the undiscounted ones have the interest rate as their drift. Right? So we have the stock, the first one has the other one, and then it has a different volatility coefficient. We call it rho. And you'll see this construction a lot where you have a parameter rho, and then you mix two Brownian motions using this rho parameter. And the reason that you do this, and then of course we have the money market account. Right, so you see there's a drift of R everywhere, and that's because we're under the risk neutral measure. Right, so you see this construction over here quite a bit. We could call this thing here for D, I don't know what to call it, maybe YT. And so the reason that you see this construction here is because of what's called, so here's Levy again. So Levy's characterization of Brownian motion. It says that this YT here, YT defined to be square root of 1 minus rho squared WTQ plus rho BTQ. This is again a Brownian motion. And Lewis characterization, there are 3 things that one should check. So one is that Y has continuous paths. You don't need this to solve the problem. I'm just telling you this because this construction here, you see here, this is something that you'll find in lots of the problems. So it has continuous paths. It's a martingale. And you see this is a martingale. And the third one is that the quadratic variation of y is t. So this is the viscosization of Brownian motion. An object is a Brownian motion if it satisfies the three properties 1, 2, and 3. So this is why you see this particular structure here. And rho here, this is what will control the correlation. It will be the case that the cross variation between S and S hat, this is going to be exactly controlled by that rho here. This will be, you take the volatility, so that will be S times sigma, and it'll be S hat times nu. Then it'll be the cross variation then between B and Y.
How are you deriving this cross variation again formula?
Well, so right, the dt terms and dB terms, right? That's how we always have it.
Yeah.
So when we look at cross variation, we forget about the dt terms.
Okay. Yeah, they do, because they don't matter when you.
They don't matter for cross variation. So then there are the other terms left, right? So we have S times sigma. That's got to get multiplied onto S times nu and then Y. And so that's that cross variation you get here, right? And then the integrands are going to get multiplied together. Right, so you have S sigma, S hat nu. This is what's going to come in front, and then the cross variation between that Brownian motion and then this Brownian motion.
Oh, and that's the, wait, what's the, oh, so the dB under Q Y is cross variation between those two Brownian motions that
Yeah.
you just.
Yeah.
Okay.
But we can work out what this is because B and W, there's no cross variation between them. And so we get here that this is S sigma, S hat nu, and then the cross variation between B and W is 0. So instead you end up just with the cross variation between B and rho B. So you're going to get a rho here and then dt.
Is the cross variation between B and W 0 because they're independent?
Yeah.
Or? Yeah. Okay.
Okay, so so that's this was just a side comment. So what do we have now is we're interested in pricing this payoff, right? So what we have to do is you have to compute a conditional expectation under Q, and then you discount it. So there's going to be e to the minus r. The time, remember the time horizon is 1. You're getting the payoff at time 1. And then the payoff is hat 1 minus is 1, and then positive part. You have to compute this this expectation. And there's a hint. There's a hint that says that you should maybe consider factoring out S1. So you can pull out, this is a constant e to the minus r, and you can factor out S1. So you factor out S1, so you're going to get S1 here. And then what's left is S hat 1 over S1 minus 1. We didn't do anything fancy here, and here comes the fancy part, because the second part of the hint says you should change measure. So introduce a new measure, so maybe we should call it Q hat. No, maybe not Q hat, Q bar. All right, so we introduce new measures by defining their radical derivatives, and we want to absorb this thing here into a change of measure. So this unit here is going to be defined as S1, and then we need to divide by the expectation under Q, because Q is downstairs. And maybe to make it a little bit easier, we could, because this is not really a martingale, but if I discount it, I'm going to get a martingale. So I could move this, I could put a minus R here and then divide by the expectation. It's going to be a little bit easier because now the discounted stock price is a martingale. I'll get S1 e to the minus R and then just divided by 0. Right. This is because ST divided by ST0, which is ST divided by e to the RT. This is a Q martingale. So if I introduce this measure, then we are in the usual situation. If I want to use Gisanov, I need to compute the conditional expectation of the radon-Nikodym derivative. So I need the radon-Nikodym derivative process. So that's my ZT. This is going to be the conditional expectation under the measure that's downstairs, which is a Q. Upstairs is dq bar dq given ft. I need to work out what the dynamics of this is. I need to be able to write, right? This is our goal. I need to write dct as minus ct something here, and then my Brownian motions. It will be dbtq, right? This here is the market price of risk. What is that question mark? That's the name of the game as usual. We can compute what this conditional expectation is though. What would we get here is, we'll start by plugging in the formula. It's 1 over S naught, and then it's the discounted stock price. The discounted stock price is 1 e to the minus R given ft. And then we use again that we have the martingale property. We use again, we have the martingale property is 1 over S naught. And then this will be ST and then e to the minus RT. Okay, so I'm close to having my DC here. This is a conditional expectation, so I know that this will give me a martingale. So to figure out what the dynamics of C are, that this is needed in order to compute this market price at risk, I'll compute DC. And so we see what we get is, I only need to worry about Brownian motion terms. So I have 1 over S naught, e to the minus RT, and then I'll have ds. This will be S sigma dBTQ. And now I can read off my market price at risk. Read off my market price at risk. Right, this here will be the first part. So this will be CT. I'll have a sigma dBTQ. Right, so the market price at risk is equal to minus sigma, because I need a minus sign here, and then it's that feature between the Z and the dB. In this case, it's going to be sigma. That's the market price at risk. And then Gisanov will tell us that a new Brownian motion is going to be given by the old one, and then plus the market price at risk. So that will be minus sigma dt. This is a Q bar Brownian motion. So now we're almost there, because now we're almost there. Like this expectation here, you combine this term and that term, and I get the radon-Nikodym derivative. Well, almost, like there's an S0 I need to correct with. So I need to multiply here by S0, and then I can divide by S0. I'll be able to write everything here as S0 times an expectation, not under Q, but under Q bar of S hat 1 over S1 minus 1. And then, of course, I need to know what happens with the dynamics of S hat, what happens to the dynamics with S1 under the measure Q bar. But this is what I know now because I know how the new Brownian motion is given. So for example, under this measure, TST, remember what it was? It was R dt plus sigma dBTQ, right? If I were to write this down, in terms of the new measure, I will need to correct this term here. I will need to write this as dBTQ minus sigma dt. I'll have to correct it over here with a plus sigma squared dt. So it will all in all become ST plus sigma squared plus sigma dBT Q bar. And I'll need to do the same thing. I need to figure out what this ratio here is. What is the distribution of this ratio on the Q bar? Well, I'll have to write the same thing here for S hat. This was S hat R dt. And then what was the formula? What's the formula? It was this one up here. It was a nu, and then it was this root 1 minus rho squared dw plus rho dB. And it's the same game as before. W stays, there's no market price of risk on this change of measure for W, so it's only this one here. This needs to get corrected with minus sigma. And then I have to add up something else here. Now what is outside will be nu rho, so I need to add nu rho sigma dt. So under that new measure, S hat t will be, we'll change the dynamics to be nu 1 minus rho squared dw plus rho dBT Q bar.
Wait,
There's a
did we
correction term.
miss a term? Yeah.
The very most important term, right? that one. Down there.
Professor, I have a few questions about this process that we just went through. So, at the end here, right, when we're changing the dynamics of ST hat,
Yes.
so that the Brownian motion is under a different measure.
Yes.
I remember we did that a few times on our home. What was the point of that? This change of measure again?
You're being asked. I mean, the question is about computing this expectation here.
Yeah.
Okay, so the hint is that you can write this expectation here in terms of this.
By substituting the plus. Or S1 minus S hat 1 minus S1 plus for that expression.
Oh, there's a plus missing. Sorry, I missed the plus. Right, you factor out S1. Factor out S1 from this thing, it goes out there. Okay, so then you have to divide by it here. And then,
yeah.
Then you absorb it into a change of measure. Right? So the expectation you need to calculate can be written as this.
Okay, so we do that to get an S1 in the expectation, and then we do some other thing so we get S1 over S0. When you say absorb into the new measure, can you explain that a bit more, this strategy?
Well, here S1 sits outside, right?
Yes.
Parentheses, S1 sits here. And then you compute an expectation on the Q. Right here, there's no S1 sitting outside the parentheses. That S1 is inside that expectation on the Q bar. Right here, there's an expectation on the Q. Here, there's an expectation on the Q bar. This S1 here is nowhere to be found over here. That's because it went into this change of measure.
I guess my question is how is it clear that this S1 term, because like the idea I guess is like after you get the hint you see the S1 term and you're like, oh, it's gonna get absorbed, but like how did we make that connection that the change of measure produces this term that it's gonna get absorbed?
You mean, how would you solve the problem if I didn't give you the hint?
No, that's not what I mean. I mean, what was the thought process to that you connected S1 with this change of measure?
But that's what I mean, right? Because this is written in the hint. So that's why I wrote the hint, that if I didn't say anything, I just asked you guys to compute this. This is a hard question. Because it doesn't look like when we talked about it before, right, we looked at call prices, right? So you had S hat minus a constant, right? You've seen how to compute that in a Black-Scholes model. And that goes back to one of the very first questions, right? If S, instead of S hat here, I would have had a constant. You would know how to compute this, because we've done that in class many times. We've done it in the homework. That would give you the Black-Scholes price. But now this is not a constant. This is another stochastic process. So how would you go about computing this? So this is just a hard problem. And so that's why I wrote the hint, like recognize that you can factor out this S1 and then do a change of measure. How did I recognize this? I mean, it's been many years since I saw this problem for the first time, but I can tell you the student who came back, he was not very happy because he didn't know how to do this one. So this
I guess my question is about, I see what, I think I see where my understanding is. So I guess my question is about the change of measure part. So is this change of measure analogous to like what we were doing in the discrete? We did something in the discrete case with change of measure too, right? With the random Nikodym derivative.
But that's what it is. Change of measure is the random Nikodym derivative.
But we have like a process now.
This is a random variable. S1 is one random variable.
Right. Yeah.
So the random Nikodym derivative process, now this becomes a stochastic process. So there it's indexed by t. So the random Nikodym derivative, this is S1 over S0. The random Nikodym derivative process is the conditional expectation of S1 over S0. Right, so that's important, right? So the random Nikodym derivative this is dq bar dq. This is this S1 over S0, which is equal to S1 e to the minus r. So the random Nikodym derivative process this is one random variable, right? This is one random variable. The random Nikodym derivative process is a Marty, right? This is this ZT. So here the time horizon is 1. Right, so this is a positive process. It starts out at 1 and it's a martingale. And at the end, C1, you're going to get this dq bar over dq. This is a process, right? So this is a family. This is a family of random variables. There's one for each t.
Okay, so with the Radon-Nikodym derivative, we're able to determine the process. What the
Yes,
process is.
right? Because you just condition.
Okay.
If I tell you a martingale, if you have, you know that it's a martingale, right? So to get from, because it's a martingale, right? The conditional expectation. So here we on the Q, the conditional expectation of C1 given Ft, because it's a martingale, this is going to give you CT. But you know that C1 is exactly that Radon-Nikodym derivative. So this is dq bar dq given Ft, which in our case is this e to the minus r conditional expectation of S1 given Ft. And I forgot, we should be dividing here by missing a term. This thing here is what I was trying to copy over here. I should have an e to the minus r here. I should have an S0 here.
If we, because like the way I remember, I'm not seeing it directly, but the way I remember the continuous version of the martingale was like you have 0 less than or equal to s less than t.
Yeah.
Right, and then you have the expected value of like zt given the filtration sub s is equal to zs, right?
Yeah.
I was wondering like how the martingale property here in the thing you just wrote shows up.
But that's what you have is more general, right? You take the upper index to be 1.
Oh, because t can be between 0 and 1.
T is between 0 and 1, right? All time.
Okay, yeah. Sorry. I just saw 1. I was thinking integers in my head, and that's why I got confused.
Oh,
Yeah.
no, I mean, this goes, so the problem, if you look at the problem formulation, right, the option pays off at time t equal to 1. So our entire time horizon is 1.
I got you. Yeah. That's the continuous interval that
Yep.
stuff is happening over. Okay.
Yeah. Where are we at? 4? 4. I forgot who asked the question. I should also, just in general, whenever there are things that I write here that doesn't make too much sense, you need to yell. Richard is doing a good job at slowing me down, and this is greatly appreciated. If you don't ask questions, I'll keep going at this pace. So it's a good idea to ask questions to break this up. There's a question about measurability. So be careful here when you say it's measurable in Q. Like measurability has nothing to do with measures. Like measurability has nothing to do with measures. Like measurability is about a sigma algebra. Right. So when we talk about random variable, a is say ft measurable. Right. What that means is a less than x is a set in ft for any x in R. Right? There's no mentioning of measures. So when you talk about measurability, it has nothing to do with measures. So I don't know if it's the word measurable that's messing stuff up, because measurable and measures, they seem to be related. They're not.
Is it because a probability space is a measurable space, or is that why it's called measurable?
Well, it's the sets inside FT are called measurable because you can measure their sizes. Because you measure Q in this case, Q goes from F1 into 0 to 1, right? And this is a measure.
Yeah.
This is a probability measure. Right, 1 here, because this is our time horizon, the problem. This is a probability measure. If, right, if Q of omega is 1, and 2, if whenever I take sets in here, Fn.
Is it the countable additivity?
Yeah.
Or
this doesn't change. That's how it always is. Right? So I need these Fn's to be disjoint. And then I need to take Q of the union. This becomes a sum of Q of Fn. But being measurable, a random variable being measurable, has nothing to do with the measures. The DZ, yep, we can do the DC. So if I have CT is equal to 1 over S0 ST e to the minus RT. So now I want to compute DZ. So if I look at DZ, this is a constant, right? So you can go outside. So then you have D of ST e to the minus RT. Right? I know this is a martingale. I know this here is a Q martingale. Right? It's a discounted stock price. So in principle, I should compute. What should I do? I should take ST, and then I should have D of e to the minus RT plus e to the minus RT dst, and then I should have the cross variation D of e to the minus R, and then you put a dot S dot T. Right, but this here is 0 because there's no randomness here, right? It's just a smooth function. This here is equal to 0. So then I'm left with the first two terms. This is 1 over S naught. Then I'll have ST, the dynamics of the money market account, 1 over the money market account. This is smooth, so you compute a derivative here. You will get e to the minus RT times minus R dt. That was the first term. And then this one here will be e to the minus RT, and then you plug in the dynamics of S. That will be STR dt plus ST sigma dBTQ. And you know this is going to be martingale, right? Because you have the discounted stock price is a martingale. So the dt terms, they must cancel out. And you see that they indeed do cancel out, right? There's a minus R here, and there's a plus R over here. So you're left with 1 over S naught ST e to the minus RT sigma dBTQ. And this is the first part here, this is my CT, sigma dBTQ. You know what? questions?
Yeah, when you expanded the d of STE negative RT, right?
Yeah.
Is that expression the dynamics of it, or is it like Ito's lemma, or what's going on with?
Well, the product rule, right?
Dynamics?
So it's Ito's product rule.
Oh, okay, I see. The two terms are from the product rule, and then the last term is from Ito's lemma.
Well, it's the cross variation, right?
Yeah.
So if I write stuff like dxt is equal to mu t dt plus, so I'm gonna put an x up here. If these are my dynamics, so I have a yt here, yt, y dt, sigma t y dt. So then if I look at the dynamics of the product, right, so now keep in mind there are Brownian motions both places. So then the product rule says that, well, you get the usual two terms. So you get the yt dxt, and you get the xt dyt. But because they're Brownian motions, look out, because there's going to be a cross variation term. There's a d, and then you have to do the cross between x and y. Right, so this is new. Right? This is our new term, and it's due to this is due to cross variation. This is due to Brownian motions. And so you can insert the dynamics now and compute exactly what this here is. This here is equal to, so you have the yt, and then dx, it'll be mu tx, sigma tx dbt. That will be the first one. And then we have the xt, and then the dy will be mu ty plus sigma ty dbt. And then comes the new and tricky term, which is the cross variation. Right, so the cross variation, forget about the dt terms. You just take the product of the two Brownian motion terms, sigma tx, sigma ty, and then you cross b, and that's going to give you dt.
The cross variation of b and b gives you dt.
What is the variation of Brownian motion?
It's t, right? If you have,
Yeah, but this term here, this is d of b.
oh, okay, so it's t and there's the d of the t. Okay.
Right,
Gotcha.
it's in d form, right? We have thrown away the integrals.
I see. Yeah. No, that makes sense. Like so we I think we said before that the Brownian motion is not differentiable anywhere, right? Even though it's continuous.
Yes.
So what we're doing here is like not really differentiation, but it's like
It's not.
similar to it.
No, we're integrating.
Wait,
These are all integrals.
all right. It's just the product rule is throwing me off because you usually have a product rule when you differentiate. Okay.
But you see, it will give me, it will simply just, what this stuff up here means is that I'll write xt, yt, I'll write this as ys times xs plus an integral from s to t of dx. Right.
Yeah.
So this would then be xs ys plus an integral from s to t. And I collect all these terms up here. So I'll have y u mu u x plus x u mu u y plus sigma u x sigma u y. This is my du term. Then I'm going to get the Brownian motion term. This is y u sigma u x plus x u sigma u y dvu. You can see how long time this is taking me to write, right? And what I
Okay,
have,
so each of those things separately is going to be integral when you finish expanding them
this
out.
stuff up here is much faster to write. And it has this meaning down here. It's just people don't do that. And that includes me. I'm not writing this out every time you see a D on the left-hand side. What that means is an integral. So we're not taking any derivatives here. We are, to the contrary, we are computing integrals. Like the derivatives are not defined, but the integrals are.
Okay, I understand now. We're integrating over this.
Integrating these things. And you might have been used to that there's this connection between integrals and derivatives, right? The fundamental theorem of calculus. Says that you take a derivative of an integral and you get the integrand, or if you can find an antiderivative. So this is out the window here. We don't have these things because there's a Brownian motion floating around, right? And a Brownian motion has no derivative at any given t. So, but I can integrate it, right? I'm integrating here with respect to Brownian motion.
Okay.
Yep. Yeah, other questions or comments? This was a long story short for this homework question. The point of doing this rewriting is, again, just to say one more time, right? You're being asked to price this payoff. Okay, so you price the payoff by computing the conditional expectation. And the problem there is it doesn't look like a standard payoff for a call or a put. But if you pull out this factor, you see this looks like a standard payoff, right? Because you have -1 here. Right? This thing here, this looks just like a call payoff. And those you have done before. Right? So you just need to know that the distribution of this ratio here is a geometric Brownian motion. And you should be able to get that as soon as you know what the distribution of this quantity, right? So you know how to adjust the Brownian motions under this measure. And you should see that this is a geometric Brownian motion. And then this is just Black's formula. That you had in one of the very first homeworks in this class. So here, this is going to lead to Black's formula. Any other questions about this? Try, we have half an hour left, so maybe we should try another one. Try another one. I had, which one was it? I had my number 6. So let me bring that one up. We can talk a little bit about it. So that was the syllabus. Here was the problem I had in mind we should try to look at. So again, always keep an eye on filtration. Here we have a B and a W. The filtration is generated by the B and the W. There are two traded securities, the money market account and the stock. And you see that the stock price, it looks a lot like what we're used to. So the first question is the model arbitrage free? Then there's this word complete. We haven't talked about that. So if there are words in these problems that you have never heard of before, don't worry about it. This is not going to be, you're not going to be hung up on completeness or incompleteness here. But you have one stock and you have two Brownian motions. So then the question is, in such a model, would you expect there to be claims that you cannot replicate? Indeed, it moves on here. So it says we consider a claim that pays out F. Can you replicate? If yes, explain how. If no, then what? And the same thing now in the last question, there's a claim that is written on the Brownian motion B instead of the stock. Can you replicate that one? Is the answer yes? Is the answer no? So let's try to work through some of these questions in this one here. So number 6, you're given two assets. You have your money market account. There's a constant interest rate. All right, so this here means that ST is equal to E to the RT, right? That's what that one means. The stock, on the other hand, is a geometric Brownian motion. Let me just look up this notation. So ST is equal to R plus sigma. Then there's a W here, dt, plus, and then there's a sigma. Again, you see this creation with the rho. That was what we had before too. So we first want to make sure that it's arbitrage free. Okay, so keep an eye on the filtration. There are two Brownian motions, so there will be two market prices of risks. Right, so we're going to be looking for dZt of the form minus Ct, and then there'll be your theta for each of the two Brownian motions. Okay, so the first question is it arbitrage free? Well, then the thing you want to look for, is you're going to find your pair theta b and theta w. Find this such that S divided by the bank is a martingale under Q with Radon-Nikodym derivative process CT. Well, we know how to do that at this point because Giordano's theorem says that you get new Brownian motions. You have the two old ones, you get new ones by adding these market prices of risk. This here will be one of the new ones. And the other one will be so what you do is you go up here, instead of dW, you would write dW plus your theta W. And now we need to correct over here in the drift. So this is coming with a sigma rho. So we need a minus Here's going to get added, so we need to subtract it, minus a sigma rho theta tw. And likewise, this dB over here, it's going to get corrected.
Professor, aren't you substituting in dwq minus theta w dt for dwt instead of the plus that you have written?
Did I get the signs wrong? I think if you have a plus here, you need a, if you have a minus here, you need a plus here.
Wait, I thought we're substituting in for d, because like when I like, aren't we solving for dwt using this equation and then substituting it in for where you have dwt in the dst in the dynamics of st?
Yeah, this quantity here is going to be my dwtq.
Okay.
Right? So I have a plus here, so I need a minus over here. And this one here, instead of dB, I want to write dB plus theta tb dt. Like this here is going to be.
The dbt is becoming the dbt plus theta tb dt.
Well, I'm correcting with the term over here.
Okay, I got you. It's because like in the previous lecture we did it like kind of differently, but it's like equivalent. It's the same thing when we correct it.
There are not that many different ways to skin a cat, right? That equality sign has to remain true, right? So if I want to add stuff here, I got to subtract it here. The same thing if I want to add something over here, I got to subtract over here. So here I'll get minus sigma, and it'll be root 1 minus rho squared, and then I'll have my theta tb, right? So what is the condition? The condition is that we need, the property we need is this ratio is a martingale, so no dt. So 0 dt in d of st over st0. It's the same thing as saying that 0 is equal to r plus sigma w minus sigma rho theta t w minus sigma root 1 minus this guy theta t b. So is that an equation we can solve? One equation and two unknowns. How many solutions do we have? Well, we have infinitely many solutions. For example, theta tb is 0 and theta tw is equal to r plus sigma w divided by sigma rho. We just need one, but here there are infinitely many. The second question is about this completeness. So we haven't really had time to talk about this, but for completeness, you check to see if theta tb and theta tw are unique. If unique, then you're going to get, so uniqueness, this is the same thing as calling it completeness. So unique is the same thing. So in our case, they are not unique. So we don't have uniqueness. We don't have uniqueness. So the model is not complete. So the model is incomplete. And what that means, so what that means is that there are, so in what's behind this word completeness and incompleteness, this means that there are payoffs that can't be replicated, that cannot be replicated. And this is what's going to come in the next question here. So don't focus too much on this because we haven't had time to go over these theorems in any great detail. The first part, yes, we have been talking about how do you create meshes such that the discounted stock price is a martingale. You get this 0 DT condition here. And then you start looking for solutions. How many solutions are there? That can be either 0, 1, or infinitely many. Okay, in this particular case, we have infinitely many, and here's a particular solution. You just need one to get the no arbitrage condition. For completeness, you need uniqueness. That's the second fundamental theorem of asset pricing. Okay, so we have no arbitrage. Now the question is, what happens in specific situations in terms of replication? So try to bring up the next question again, question 2. Now you're looking at a claim f of st, and the question is, can you replicate this claim? If the answer is yes, tell us how to do it. If the answer is no, you need to tell us why you cannot replicate it. Okay, so that one we can do. So this is a function of st. Right, so we want to have our wealth. We want to have our wealth xt to be such that it's equal to this function of st. Right? That's our usual replication. And so if I want this to happen, I will now discount. This is the same as requiring that xt divided by the money market account is equal to f of st divided by the money market account. Right. So if this is true, so if star holds, we must have that the conditional expectation under one of these measures Q from the first question. Right. On one hand, this is the martingale property of the discounted wealth process. Right. You take the wealth, you discount it, you get a martingale. On the other hand, if this is true, then you get a formula for xt. So if it is to work, there's only one choice. X of t must be given by st0 times the conditional expectation of f of st divided by st0. So then the question is, does it work?
Should that second, the thing in between the equality signs, should that be, yeah.
Right, that's the martingale property. You discount the wealth, you're going to get a martingale. So here we're discounting the wealth, conditioning. Right, this one here is a martingale. Okay, so how do we see if something like this can be true? Well, we've been in this.
It kind of feels like that backward induction thing.
But that's exactly what it is. It's just in continuous time. It's just in continuous time.
Okay.
So this here is a martingale. This is a Q martingale. Like this is one of these Levy martingales we've had many, many times. how do we attack this thing? We're being asked to give a formula for delta. Well, the way to go about it is to find the PDE. And this is a martingale. Okay, so we could start by attacking that one. Right, so we're going to have what's it going to? So xt discount is a martingale. Okay, so let's call this here something. So we're going to say that this is htst is equal to, we want this thing to be equal to this martingale. All right, this is a martingale, so we want this thing to be that. Okay, so let's find a PDE for it. So first we put t to be capital T. Then we're going to get h t is capital T is equal to f is capital T divided by s capital T. Right, this is equal to e to the minus rt f of st. Right, so the function h at maturity should be e to the minus rt f of x. Then the second part is when we're less than t. Then we're going to get a PDE. We're going to get the PDE because we know that this ought to be a martingale. Right, so we'll apply Ito's lemma to compute the dynamics.
Wait, about the first part.
Yeah.
Right. Why does this simplify to how do we get the value of h big T s sub big T?
This is the formula, right? You take
Yeah.
t equal to capital T. Look what's on the right hand side. Little t equal to capital T.
It's just measurable, and
Yeah.
then it comes out. Okay, I see. And then the e to the negative rt just comes from
This one here.
substitute.
This guy, right? The money market account.
Okay, yeah. I see.
Money market account. So now we get d of this thing. We use Ito's lemma. So it's the first derivative, and then the second derivative.
Oh, the money account is just an ordinary differential equation. That's why it's like that, right?
And it's right here.
Yeah, I just saw the connection between, because that's just like you just integrate on both sides and you get, okay. Yeah. I got you.
Yeah, I mean, the new stuff here compared to what you have learned in other classes, it's not the first part, right? This is just an ODE, and it's a linear ODE, right? It's an exponential function.
It's like the first thing you learn in the differential equations class. Yeah.
But this one here, you have probably not seen, right? Because there is, instead of that dt over here, you still have that dt. Like, had this part not been there, this would have been something you could have been taught in that class too. You have ds is equal to s times something dt. This is going to be an exponential. But now we have a dv over there, right? That's different. You've probably not seen that in a differential class on ODE.
But so isn't the money market, isn't the st to the 0, is that a stochastic process too? Or
well,
it isn't?
Yes, it is, but it's just a very simple one, right? There's no randomness about it.
So that's why you can just integrate on both sides and then have this ordinary differential equation.
You can do the same thing if sigma is equal to 0. You can do the same thing, right? We'll just figure out how to do that. If I were to give you dst is equal to st r plus sigma wt dt, right? Drop the second part.
Right.
You can do the same thing. Right, so st would be s0, an exponential, an integral of r plus sigma wu du. Why? Because if I take the derivative with respect to time of this st here, what are you going to get? Well, it'll be S0. Derivative of an exponential is going to be the function itself times the derivative of what's inside. So that's going to be R plus sigma WT.
Okay.
Right, and what you have here, this is exactly ST. Right, so you get the derivative of ST is equal to ST times R plus sigma W. Well, that's exactly what you have.
I see. Okay.
The problem is you can't, if instead of du here, if instead of du you write dB here, then this is it. You cannot just put, this is not true. You cannot just substitute like that. It won't work with this guy. What will work is if you put minus a half, and then you need some correlation to make up for Ito's lemma. So you need an R plus sigma WU and then a square du. And this one will work. And the way to see that is, okay, so now we're veering off topic here, but right, so we're claiming that S0 e to the, what should we call this thing up there? AT. AT is all that mess up there. Minus a half, and then this R sigma W squared du. Right, if I look at dA here, so now I'll throw away the integrals. So I throw away the first integral, I throw away the other integral, R sigma WT squared dt. So I need this thing to use Ito's lemma. I need the credit gradation of A to use Ito's lemma. Credit gradation of A, I need to throw away the dt terms and square the integrand. R plus sigma WT squared, and then credit gradation of Brownian motion, this is T. So now I can use Ito's lemma to compute D of this thing. Right, so E2 will give me the ds0 e to the AT. Yeah, this is S0. Right, and then it would be, well, I can write it out like this. Use Ito's lemma, we need two derivatives. Right, we need two derivatives, so we're going to get S0 e to the AT DAT plus, then the derivative of exponential function 2 times is the same as just 1 time. So this is e to the AT, d credit gradation of A. Like that's the new term that you didn't see in the ordinary differential equations class. And so here you'll get S0 e to the AT dA. Well, that's the mess we have up here. It's R plus sigma WT dBT minus 1/2 R plus sigma WT squared. So that was that term, and then we need plus 1/2. That term goes outside. And then credit gradation, this is R plus sigma WT squared dt. Right, so the miracle happens. This term, that term cancel. And you get exactly that the dynamics of this thing is equal to the same thing times R sigma WdB. And that was what you wanted up here. So this here is UST, this here is UST. So we can solve these equations here. It's just, you cannot just proceed and treat Brownian motion like a dt. This will never work. And here you can see there's suddenly this correction term that has to come into play for you to solve an equation where ds is equal to sr plus sigma w dB. So you have to use Ito's lemma, and that involves computing this quadratic variation, and that's needed because there's a Brownian motion there. And this is why you get this extra term down here.
I see.
Yep, go ahead. Go ahead.
No, I said I see. I understand.
Okay. All right, so let's try to get back. Time is running out, guys. So let's try to get back and finish up this problem here. What were we? Forget where we were. Oh, we were working on, yeah, it's always Ito's lemma. We're working on Ito's lemma here. Right, so we have the dynamics of this thing. So now there's a time component too. So we need a derivative with respect to time. And we need one derivative with respect to the stochastic process S. So that goes in there. And then we have Brownian motion inside S. So we always need that extra half. And then two derivatives, T, ST, and then the quadratic variation of S. And okay, so now we plug in terms. H1, T, ST. What else do we have? We have H2, T, ST, and then DST. DST depends upon what measure we're under. So we're working under a risk neutral measure. So there's no DT terms inside DS here. We just need to focus on S and then sigma rho, S sigma rho. Okay, so let's put that in there. S sigma, and then we had a rho dWt q plus root 1 minus rho squared dBtq. Then we have plus a half H22 TST, and then the quadratic variation is going to be we square the integrand, so that'll be ST squared sigma squared. We square that and we square that. It's all going to give us a dt. And what I want it to be is 0 dt, right? Because H, that's going to be a martingale. It's a Levy martingale. So 0 dt. And what's the volatility? The volatility is H2 T ST ST sigma, and then the two Brownian terms. Okay, so if I want this 0 to be here, there are a bunch of dt terms that must cancel out. So we're going to get the PDE. We're going to get the PDE. PDE is H1 Tx plus 1/2 H22 Tx x squared sigma squared. This must be 0. Right, so give me a function. Give me a function such that at the end, this is my terminal condition. It satisfies, well, this here is called the heat equation. It satisfies the heat equation. So how do I create from all of this? How do I create from all of this my delta? This is the question, right? So if I do this, I'm going to get that, I'm going to get that my wealth. Slides. Like this here's what I have called h of t st. So my discounted wealth is equal to this. Okay, so how do I get my investment strategy? Well, I compute the dynamics of my wealth process, discounted. So I know that the dynamics of the discounted wealth is going to be my holdings times the discounted stock. I'm interested in what this delta is. And we can write out what this here is. This was delta t, the discounted stock. We've had that a few times. This was st over st naught, and then sigma rho dwtq plus 1 minus rho squared, square root of 1 minus rho squared dbtq. I am interested in figuring out what that is. Well, I know that this is equal to d of h st. And I know what that's equal to because we had it up on the previous slide. This was h2 t st sigma, and then this long mess rho dwtq plus root 1 minus rho squared dbtq. And so now we can get what delta is. I solve, I'll get, what will I get here? I'll get delta t. I need this thing to be equal to that thing, so a lot of it will cancel out. I'll get delta t is st0 times h2 t st. Where h is that solution to my PD. I have the terminal condition, and I have the PD itself. Alrighty, guys. This was I had hoped to do one more problem, but we'll do one more problem on Thursday. I had in mind to do problem 7 as well. So we did most of problem 6. We'll do some more problems on Thursday. Already there are office hours this week, and then next week is when we'll start on the exams. Are there any more questions or comments before we call it a night?
Is there like somewhere I can review that differential equation stuff you just wrote down about the the thing we just did like 5 minutes ago? Because I feel like a lot of this will become clearer to me once I see the connection to the differential equation.
I mean, so you were good on the one without, if I put dt there, you were good. Is that correct?
Yeah, I think so. I mean, like, hold on, let me see. But I mean, if you put dt there,
yeah,
is it just a separation of variables one, or?
But if you put dt there, right? This works here, right?
Okay. I think I have to go over it once, but yeah, I trust that would be fine. Yeah.
Look, man, you take the derivative. So if you put dt there, you put a du here, right? So now all this stuff is not there. You take the derivative with respect to t. What do you get? You get S0, derivative with respect to t, exponential's derivative is exponential. You compute the derivative of a time interval, you get the integrand evaluated at the upper limit. That's what you have here.
Okay. Okay.
There's nothing fancy here at all. It's just a linear ODE.
Okay. Yeah. I see
A
that.
linear ODE, right? If I tell you that f prime of t is equal to g of t,
Mhm.
and f at 0 is equal to 5, and there should be an f over here, right? What is the solution to such a linear ODE? Well, it's going to be f of t is equal to 5 times e to the interval from 0 to t of g of s ds.
Is there no wasn't there like a term we multiply by the r plus sigma wt term too, or?
But that's your f. I know f is s here, right? And then g is just that thing there.
Okay. Yeah. I see it.
You just integrate and compute the derivative of this one. You're going to get exactly this one here.
I see. I gotcha.
So there's nothing fancy about this. Is just linear.
Yeah, it's the regular stuff.
Now, had I
Yeah.
put a square here, then it's a different story, man. It's much harder. That's what we talked about, I think, maybe a couple of times ago before Thanksgiving.
Okay. I'll look over it. Thank you, Professor.
I'll see you guys. Office hours are the same as always. Back to the usual. I forget if I would do a change on for you guys last week. I don't think so. The office hours this week are 9 o'clock on Thursday and Friday. So let me write that here. 9 Thursday plus Friday. Alrighty, guys, have a good night, and I will see you on Thursday.